and welcome to my YouTube channel. I'm Mariel Alcazar, a mathematics enthusiast with a deep passion for exploring and sharing the beauty of math. Here in this channel, we dive into mathematical concepts, solving problems, and uncovering the fascinating patterns that shape our world. In today's tutorial, we're going to prove the Pythagorean identities, break it down step by step to make it easy to understand and apply. Whether you are a student, a teacher, or someone curious about math, there's something here for everyone. Derivation of trigonometric formulas. Today, I'm going to prove the Pythagorean identities. Now, these are three identities that are used commonly in analytic trigonometry, which means algebra-like trigonometry. Now, these are called identities because any angle can be substituted for theta. They are not trigonometric equation in which only one or a certain sets of angles. It works in them any angle substitute in for theta works in the identities. So these are very important. Why also are they called Pythagorean identities? Well, think of a right triangle and think of a Pythagorean theorem. We have a squared plus b squared equals c squared for the Pythagorean theorem. If you look at all of these, they have the same sort of form if you realize that 1 squared is equal to 1. So that's why they're called the Pythagorean identities. Now, on to proving them, we're gonna prove them one at a time with this right triangle right here. Okay, keep in mind the Pythagorean theorem, we will use it. Let's start with the first one. Sine squared theta plus cosine squared theta equals 1. What I'm going to do is I'm going to define a specific angle that I'm going to use in my proof. This one, this acute angle theta. So what I'm going to do is I'm going to set up an expression for each of these trig function in every first Pythagorean identity. Sine theta when it comes to this triangle would be opposite over hypotenuse, so b over c. Similarly, cosine theta, which is another term in the expression, is equal to adjacent over hypotenuse, so a over c. Now I'm going to ask to identify the square both of these and add them together. So I will get sine squared theta plus cosine squared theta. I'm gonna write what those equal the equal b squared over c squared plus a squared over c squared. Now, I'm going to combine these two fractions and it can be done very quickly because of the denominators being the same. So this is going to equal b squared plus a squared over a single c squared. But recall the Pythagorean theorem that I wrote over here. A squared plus b squared itself equals c squared. So what I have on top is c squared. Now on the bottom, I also have a c squared. These cancel each other and I get 1 thus sine squared theta plus cosine squared theta equals 1. We have proved the first trigonometric identity. Now for the second one, 1 plus tangent squared equals secant squared theta. Okay, so what I'm gonna do for this is I'm gonna write the expression for tangent theta and secant theta. Tangent theta would be equal to opposite over adjacent, so that b over a secant theta would equal to the reciprocal of cosine. That is how secant is defined. So secant theta would be equal to a hypotenuse over adjacent. So c over a, which is the reciprocal of a over c. Cosine theta, now according to the identity, we're going to add 1 plus tangent squared theta and it's going to be equal to secant squared theta. So let's do that. 1 plus tangent squared theta, this is equal to 1 plus b squared over a squared. Now comes the algebra. We're going to get a common denominator here. We can often start that process by seeing the first number as a fraction by putting it over one that doesn't change anything about its value. So as you can see, this fraction by least common multiply needs an a squared and the other one already has the a squared. So I'm gonna have to multiply this fraction by a squared over a squared. So I get that 1 plus tangent squared theta equals a squared over a squared plus b squared over a squared. And I can combine these two fractions how into one because their denominators are the same. So I have the common denominator on top 5. A squared plus b squared. Okay, again, the Pythagorean theorem says the numerator itself is equal to c squared. Now, that might look familiar to you if you jump back up here. It's equal to this squared. So it's equal to the second theta squared equals second squared theta. So how I have a direct connection between 1 plus tangent squared theta and second squared theta. We have done the proof of the second trigonometric identity. Example of formula application. Cosine is equal to 8 over 17. And let's say the angle theta is between 3 pi over 2 and 2 pi. So based on this, what is the value of sine? So let's use the same formula. Sine squared plus cosine squared is equal to 1. So we need to find the value of sine. Cosine is 8 over 17. Eight squared is 64, and 17 squared is 289, and 1, let's rewrite it as 289 divided by 289. Any number divided by itself is 1. So we got to subtract 289 by 64. So sine squared is equal to 225 divided by 289. Now, let's take the square root of both sides. So sine theta is going to be the square root of 225 is 15. And we know the square root of 289 is 17. So now, which sign should be used, positive or negative? So if the angle is between 3 pi over 2 and 2 pi, what quadrant it is located in? Now keep in the mind 3 pi over 2 is equivalent to 270. 2 pi is 360. So it's located in the quadrant 4. And in the quadrant 4, sine is negative but cosine is positive. So therefore, sine is going to be negative 15 over 17. In this particular example, so that's the answer. Real-world connection of trigonometric concept. To determine the height of the building using the given information and the Pythagorean identity for trigonometric function, we are given the distance from the observation point to the base of the building, which is 30 meters. The angle of elevation to the top of the building, which is 45 degrees. We need to find the height of the building. The horizontal leg is the distance from the observation point to the base of the building, which is 30 meters. The vertical leg is the height of the building, which is we need to find. The angle between the horizontal leg and the hypotenuse, the line of the side to the top of the building, is 45 degrees. The tangent of the angle is the right angle is the ratio of the opposite side, the height of the building, to the adjacent side, the distance from the point of observation. The tangent of 45 degrees is tangent 45 degrees equals 1. So we have tangent 45 degrees, height of the building 30. Since tangent 45 degrees is equal to 1, we can set up the equation of 1 equal to height of the building over 30. To find the height of the building, multiply both sides of the equation by 30. Height of the building equals 30 times 1 height of the building equals 30 meters. The Pythagorean identity for tangent and secant is tangent squared theta plus 1 is equal to secant squared theta. For theta is equal to 45 degrees, tangent 45 degrees is equal to 1 and secant 45 degrees is equal of square root of 2. Therefore, tangent squared 45 degrees plus 1 is equal to secant squared 45 degrees. Using the identity 1 plus 1 is equal to square root of 2 squared, 1 plus 1 is equal to 2. In this tutorial video on Pythagorean identities, we cover the following key points. First, introduction to Pythagorean identities. We introduce the fundamental Pythagorean identities. The second one is derivation and proof. We demonstrate how to derive these identities using the right triangle and basic trigonometric definitions. We showed step-by-step proofs to ensure a clear understanding of where these identities come from and why they hold true. The third one, practical applications. We explore how these identities can simplify complex trigonometric expressions and solve trigonometric equations. And the last, problem-solving examples. We worked through several example problems, showing how to apply the Pythagorean identities to simplify expression and solve equations. We encourage viewers to practice these examples to solidify their understanding and proficiency. Understanding Pythagorean identities is crucial because they are foundation tools in trigonometry that simplify solving problems across various domains in mathematics, physics, and engineering. Mastery of these identities enhances problem-solving efficiency and accuracy.